Hey, welcome to the Explainer. Today, we're going to tackle a really clever mathematical technique for solving some seriously stubborn equations. It's all about flipping a problem on its head to find an answer you couldn't see before.
All right, let's kick things off with the core problem, right? You've got these equations that describe our world, from how planets move to how populations grow, and sometimes they just refuse to be solved with the usual tools. So what do you do then?
Okay, to really get a grip on this, let's actually see the problem. Sometimes visualizing what you're up against is the most important first step.
Okay, so picture this. You're standing in this huge field, and at every single point, literally everywhere, there's a tiny arrow on the ground telling you which way to go. That's what a slope field is. Now, you could wander around on countless different paths, right? But our job, our whole mission, is to find that one specific path that starts at that little red dot. How in the world do you trace it?
So what we're looking at here has a fancy name, an initial value problem, or IVP. And it's really just two pieces. You've got the differential equation, that's the rules of the road, the thing that draws all those little arrows. And then you have the initial value. That's your starting X marks the spot on the map.
And this is where a mathematician named Charles-Émile Picard had this moment of absolute genius. See, instead of trying to bulldoze his way through the problem head-on, he found a kind of back door, a way to completely transform it.
So check this out. On the left, you've got the problem we started with. On the right, that's its alter ego, an integral equation. Now, Picard proves something incredible. These two are one and the same. They look totally different, I know. But if you solve one, you have automatically solved the other. And that little switch in perspective, is everything.
And don't just take my word for it. The math itself spells it out perfectly. The key takeaway here is that solving our original, tricky problem is exactly the same as solving this new continuous integral version. And guess what? This new one is way easier to get your hands on.
So why does this matter so much? Well, this new integral form is amazing because it lets us build the solution piece by piece. We don't have to find the whole thing in one giant leap. We can start with a really simple guess and just refine it over and over until we get the right answer.
And this step-by-step process is called successive approximations. I love the analogy of a sculptor. You start with just a big, rough block of stone. That's our first super simple guess, maybe just a flat line. Then you run it through this process, this mathematical machine, and it chips away a little piece, giving you a slightly better shape. You take that new shape, run it through again, and it gets even more refined. You just keep repeating, and with every pass you're getting closer and closer to the masterpiece hidden inside.
Okay, enough talk. Let's see this thing in action. We're going to use an example and literally watch this method build a super famous function right in front of us. This is where it gets really cool.
All right, so here's our problem. dy dx equals y. And our starting point is y equals 1 when x is 0. So what's our first guess? Our blackest stone? We'll start with the absolute simplest thing we can think of, the constant function y equals 1. Just a flat horizontal line. Okay, so we take that guess, y equals 1, and we plug it into our integral equation. We turn the crank once, and what comes out? We get y equals 1 plus x. Boom! Our flat line now has a slope. It's already a better approximation.
All right, round 2. We take our new answer, 1 plus x, and feed it right back into the machine. This time it spits out another piece, x squared divided by 2. See what's happening? Our straight line is starting to curve, getting even closer to what the real solution looks like.
Let's go one more round. We take our brand new curve and plug it in. And, yep, you guessed it, out comes another term, x cubed divided by 6, which is just 3 factorial. There is definitely a pattern emerging here, isn't there?
Okay, pause for a second and just look at this series we're building. 1 plus x squared over 2 factorial. Does that look familiar at all? If you spent any time in a calculus class, your spidey senses might be tingling right about now.
That's right, it's the power series for e to the x. I mean, how incredible is that? Picard's method didn't just give us a close enough answer. It literally constructed from the ground up one of the most important functions in all of science and math. It built the exact solution.
So, okay, we've seen that it works, and it's pretty darn elegant. But what's the real point? What's the deep significance of this method? Why do mathematicians care so much about it?
Because you might be sitting there thinking, okay, that's a cool party trick, but couldn't I just use a computer to solve this? Right? Is this just a really complicated calculator?
And the answer, as our source material makes crystal clear, is a resounding no. The true power of this method has almost nothing to do with calculation.
It's about something much, much bigger. It's about proof.
See, this whole process is the bedrock of a huge theorem in math, the Picard-Lindelof theorem. Its job isn't to find the answer, but to prove with 100% certainty that for a massive class of these problems, a solution exists at all. And not just that, but that the solution is totally unique. It's not about finding the path in the field, it's about proving that there is one, and only one path there to be found.
So, at the end of the day, what Picard's method does is it takes this messy, practical problem of, how do I calculate this, and turns it into this powerful foundational proof. It gives mathematicians the confidence to know that the things they're searching for aren't just ghosts, they're real, they're unique, and they're out there.
And that just leaves us with this one kind of cool final thought, right? Picard's method shows us that sometimes the hardest problems aren't cracked by more power or just grinding it out. They're solved by one simple, elegant twist in how you look at them. And it really makes you wonder, what other huge, unsolvable problems are just sitting there, waiting for someone to find that one clever trick?